Hey folks, I'm Pete Delvecchio. I'm the product line manager for the Tomahawk 5 family. In our previous presentation, we talked about Broadcom in general and Tomahawk 5, some of the general features of Tomahawk 5. This presentation will focus on some of the features of Tomahawk 5 for AI ML. Okay, so just to recap some of the high-level features, again, world's fastest switch chip, 51.2T, very low power, monolithic 5-nanometer implementation. Very flexible, low power, low cost, physical connectivity. So we have a very unique SerDes architecture that's specifically designed for networking applications. What we'll get into in this presentation is how we accelerate AI ML workloads. And as we discussed in the previous presentation, there are features on the chip such as single pass, VXLAN routing and bridging you can use for both virtualization of standard compute and storage and for now AI ML. Okay, so there is a narrative being pushed by some other folks in the industry that if you were going to use a network for AI ML, that you want to use, say, something like InfiniBand or say OmniPath. Now, if you looked at this is a study that was done by Los Alamos National Lab, where they compared native Ethernet versus InfiniBand, and you see as far as latency and as far as bandwidth, there were some advantages. However, there is a huge community behind Ethernet. One thing that was added is RoCE or RDMA over Ethernet. And if you saw the build with that dashed blue line, what you see is that once you add RDMA over Ethernet to Ethernet, or RDMA over Ethernet, you wind up getting virtually identical performance. And one other important point here is that you'll see because of the fact that Broadcom tends to lead as far as switch bandwidth, as far as radix, because there's a broad ecosystem behind Ethernet, you almost always wind up with Ethernet having significantly higher bandwidth and higher radix as compared to these more proprietary interconnects like OmniPath and InfiniBand. So you'll actually wind up with better performance at any point in time with Ethernet compared to these other technologies. So we did another study with one of the leading hyperscalers where they were trying to figure out for themselves as they're adding AI ML acceleration into their networks, should they continue to use Ethernet or should they now have a dedicated network that uses, say, InfiniBand? And this is a test they did on a cluster using InfiniBand switches and using some previous generation Tomahawks. And what they found, this was a test using all reduce, all-to-all collectives using a nickel library. And this is at the same bandwidth point. I think this is with 100 gig E Ethernet versus 100 gig E InfiniBand. They actually found that you wind up getting higher throughput for these larger message sizes that are typical of AI ML workloads. And if you look overall at all the main factors you would choose or examine for AI ML networking, as far as the bandwidth of the fabric, the port speed, the radix and the bandwidth is very important because you want to be able to minimize the number of hops through the network. So you have a large number of AI ML nodes you want to interconnect. You'd like to be able to do that with one hop or maybe two hops through the network. So the higher the bandwidth, again, as we saw in the previous presentation, if you had a lower bandwidth switch, you might have multiple tiers of switches, which of course increase the latency, increase the power for the networking. So overall, these factors as far as load balancing, as far as telemetry, you'll see that Ethernet meets or exceeds anything you'll get from the proprietary single source technologies such as InfiniBand. So what makes the AI ML networking unique? How is it different from standard DC workloads? So one of the main things is, if you look on the right-hand side, you'll see that applications go through this repeating cycle of, they do a large amount of compute, then they communicate the intermediate results, they'll synchronize, and then repeat this process over and over again. So you wind up with thousands, tens of thousands, hundreds of thousands of jobs that are doing this synchronously. So what happens is here, when you're transferring these flows, first off, they tend to be very large flows with less entropy. So if you're figuring out how to do load balancing, you'll look at the entropy of the packet. So you'll look at the source dest IP, source dest MAC, maybe the port, and then figure out how to load balance. Now, in a standard DC networking application, you have a lot of CPUs that are running a lot of different workloads. So you have a lot of different size of flows. You have a lot of entropy in those flows. So here you have a lot of flows that are coming onto the network simultaneously. So you could wind up actually with your links getting saturated almost immediately because you have all these jobs that are completed their task and they're now trying to dump all the traffic onto the network simultaneously. So here you have, again, a large portion of the bandwidth is these huge elephant flows. You have fewer flows with less entropy. So it's very important that you make good decisions immediately when that traffic hits the network. And you be able to do load balancing, not just based on the entropy of the packet, but also on the characteristics of the network. One other note here is that the penalty is extremely high if you have poor path selection initially. So the progress of this whole job. So again, you've got these many thousands of nodes that are computing a task, and until all the data is transferred between all the nodes, I mean, you really worry about that that flow completion time, the tail latency of the last packet, because until all the data is transferred, until all the jobs are synchronized, you can't advance to the next computation step. So it's very, very important for AI/ML to load balance properly and do that quickly, because again, your congestion control algorithms don't have a chance to catch up because your links are saturated so quickly. So some of the features we have, so what we call cognitive routing. This is a suite of capabilities that improves the routing for all workloads, and in particular accelerates AI/ML workloads. So I'll get into that in pretty good depth in subsequent slides. Advanced queuing and buffering. So we'll get into the queuing and buffering architecture, how that provides some improvements as far as minimizing packet drops. Last presentation, we talked a bit about the instrumentation. So here, again, it's a very flexible instrumentation. The types of congestion control, types of load balancing that you do for AI/ML, again, because the workloads are different, will be, you might need to have different types of telemetry compared to what you had for standard, DC, compute and storage. High precision synchronization. So we have SyncE, we have 1588 built in, class C, so very accurate time stamping. You can use, again, for congestion control, for synchronizing your jobs. And then we also have very fast link failover. So in less than 500 nanoseconds, we can detect a link failure and we can steer the traffic onto a new link. Now that's really critical, again, for AI/ML, because in AI/ML, again, if you drop packets, if one of the jobs, if one of the communication phases is held up, it holds up the progress of all the jobs.
A question for you on the link failover.
Yep.
Is that a hard failover, like you've lost link, or can you detect a soft event in there? So you've lost connectivity for whatever reason, or you've lost, you've got a unidirectional traffic all of a sudden, or anything like that that would cause it to sort of fail with a link light on?
Yeah.
Are you able to detect at that level, or are these just hard drops?
So what we talk about here is if you had that hard drop, but we do have capability to figure out, is the link just kind of dicey? Is it something where it's a short term? So there will be a timeout here where you can say, okay, I want to wait a certain amount of time. It's like we can do it in 500 nanoseconds, but you might say, hey, I want to give the link a chance to stabilize. Maybe I think it's a burst error that somehow got introduced into the network. So in that case, yeah, you can set a timer for that. So we actually have a number of features to actually detect if a link is potentially going to fail. So once you start using 50 gig PAM4, you pretty much universally have to use some sort of forward error correction. And with that forward error correction, you'll have a certain number of correctable errors in a certain code word. So what you can do is over time, and we can do this in real time as the chip is working, we can look at the number of correctable code word errors, and we can say, okay, this link is getting kind of flaky. So I know it's getting near the FEC limit for that link, and you can potentially proactively swap out an optic if you think it's going to fail. Or you could use that, as you were saying, that you might say, okay, this link, normally it's pretty solid, but for one reason or another, it had a fail, but I think it's actually going to recover quickly, so therefore you wouldn't do that failover. Okay. So there's actually quite a bit of monitoring in real time. We can detect the SNR in real time. We can detect the code word errors in real time, and use that to potentially predict a link failure that's about to occur.
Stephen brought up a really great question in chat. When you guys were looking at your data of RDMA over Ethernet and InfiniBand, was there any analysis done of the host CPU load for serializing that data onto the networks?
Well, I think that's somewhat independent of the network, because that can be done, similarly, it can be done either on the host CPU or it can be done on a NIC. Very often that would be, because it is something that does have to happen in real time. So usually if, those RDMA type operations would be offloaded onto the NIC. Since it is, direct memory access, it's something normally you wouldn't have it going through the CPU and the networking stack on the CPU. So kind of by definition, since it's, remote direct memory access, it wouldn't be the load on the CPU because, again, it's direct where you have the memory being accessed through the NIC onto the network. Okay, so get into cognitive routing. So we don't talk about all the features. We haven't announced all the features yet. But again, this is a suite of capabilities that adds intelligence to the routing decisions. One thing that is really powerful is we do now what's called global load balancing, or GLB, where previously we had DLB, or dynamic load balancing, where again we would look at the entropy of the packet, maybe do a hash on that, determine what link to send the packet onto, and we'd also look at the link quality. So we'd look at the queue, queue depth. We'd look at how heavily loaded that link is. But those are all local to the switch. What we can do here is actually take data from downstream, and we can feed that into the upstream switches. So now those upstream switches know the quality of the path throughout the network. So when it's making its load balancing decision, again, it's not just based on a hash. It's not just based on local link quality. It's also looking at the total path quality through the network. We also do elephant and mice flowlet steering. So just because you had a flow that's pinned onto a certain link, now if you have a flowlet, so if you have a pause in the packets, we can take that. This is a programmable duration. You could say this flowlet, I want to have go onto this link, and then the second flowlet can go onto a different one. Yeah.
Hi, can you talk a little bit more about the global load balancing? Is this a situation where you have, a Tomahawk in, say, switch 1 talking to another Tomahawk in switch 2, so that you need to have that particular architecture throughout? Or is this something that each individual switch chip can kind of work on independently? Is there an intelligence throughout the network that you are able to gather the information about the link quality, or is this an individual thing?
So there would have to be some intelligence that's pushed from a downstream switch onto the upstream switch.
Okay.
So it's not the local switch, which is polling that, but it would be a downstream switch. That could be a Tomahawk 5. That could be a previous generation switch that would in turn send some data on the queue status. It would send that upstream. So it is something where there's no centralized controller. It is within the network. But it would be something where, it's basically Tomahawk 5. The new thing we have here is the ability to take that global information, then use that in the pipeline for that traffic steering decision.
Okay.
But there would need to be some kind of intelligence from a downstream node to provide that link, quality metric up to the upstream node.
Okay. So you mentioned that there's no controller involved in this. Can you talk a little bit about, I guess, well, your slide says it all, kind of the brains of the whole global load balancing, and where and how does that intelligence arise in terms of being able to just, look at the entire system and be able to come out with this global load balancing?
Yeah, sure. Yeah, so it's basically, it would be the network of switches that, again, you don't need to have any data, any telemetry that's sent to a centralized controller. It's basically this network of switches within, say, like a switch complex that, the downstream switches, normally you'd see, in a closed network, the most important thing is that once you're at the top of the tree, there's only one path to a destination. Mm-hmm. So what you'd like to do is look at that tree and then say, okay, this particular path, since I only have one path I can go on to, I want to feed that information back to the upstream switches. So it would be those upstream switches that would say, okay, my outgoing links have congestion. So they would in turn, they'd have some sort of trigger that they would send, a packet, an out-of-band packet to the upstream switch to determine or tell it, okay, this link that you're about to send onto, that there's only one path down to the destination, that link is congested. So it's basically, intelligence arising from the whole network with something running on a downstream switch, looking at the state of all the queues, looking at the state of all the outgoing links, and feeding that information to the upstream switches.
Okay, so like in your architecture, you've got, we'll just take Clobe because it's easy. Mm-hmm. You've got 2, let's say 4 spines, and you've got 10 leaves, mm-hmm. and spine 1 is congested going down to leaf 1.
Yep.
So then it would be, are the spines talking to each other and they're saying, spine 1 is announcing I'm congested, send to spine 2 or spine 3? Is that how it's working, or?
It's basically between, link partners. So, anytime that if you had, say, a leaf switch going up to a spine, that spine says my outgoing, links are congested, that spine switch would in turn send some congestion information to that leaf switch.
Okay.
So it's not so much, each tier that's communicating to each other, but it's more, what is the actual path the packet's going to take? And then those downstream switches propagating the information upstream.
Okay, so basically spine 1 saying I'm congested, so then if I'm trying to send to leaf 1, I get the message spine 1 is congested, and I'll send to spine 2.
Yeah, so basically then that's that leaf, that's in the intro to the network or upstream of the network would say, okay, I know that I have this path, I've got 64, I got however many upstream links. I know to get to this destination here, I can go to any of these switches. And this switch, the spine switch here, told me that that link is going to be congested. So then it would decide, okay, I'm not going to send to that switch. I'll send it to an alternate spine that has a clear, uncongested link.
Is it just one hop that switches talk to the next guy, or can that be passed on, or
It can be passed on.
summarized on?
Yeah, I mean, you'll wind up getting most of the benefits even with a single hop, but we can
I think
do.
we all have spines and leaves everywhere, right?
Yeah.
So, I mean, we only need 2, but I mean,
Yeah.
there's certain legacy networks that are going to have, stacks of switches.
Yeah, so that is flexible. It is programmable, where you can say, is it just, one hop you want to go? It gets certainly a lot more complex, more hops that you have. And you'll wind up actually getting most of the benefit with a single hop. But that is something that is flexible.
So is there, I assume there's some way to say, I only want to hear from my switches in case somebody, maybe you're in a shared environment, and you have Broadcom here and Broadcom here, but you don't necessarily want to take instructions from, the upstream provider or something. Is that, is there?
If we thought that, if you're operating a network, heterogeneous network, and there was good information provided, you might as well leverage it. So far.
Until the hacker gets in the mix, once all the traffic put out a certain path for a nefarious reason. That's what I'm
You
looking
can
at
certainly
from a
limit
security
that.
point of view.
Yeah, no, we can secure the packets going back and forth. So yeah, that is. Yeah, you can make the choice as an operator to do that. Okay, let's get into the shared buffer. So again, one thing we mentioned a bit during the previous presentation is, we do have a fully shared buffer. The high-level architecture is we have, a large number of parallel ingress pipelines feed into the shared buffer, and then that shared buffer again goes to the egress, that goes out to your port macro on the output port. One alternate architecture you see is these, slice buffers that, normally like one of the competing architectures will have an egress slice buffer. Well, they'll wind up taking the full buffer, so you'll see a certain buffer size quoted, but then if you actually look at the how that's used, it tends to be used on the tied to a certain egress pipeline. And we showed here, this is a commercially available switch, with this architecture, and we see that the Tomahawk architecture can give you up to 10x better packet burst, packet absorption. So this is one of the main things, I think, as far as absorbing bursts, making sure you don't drop packets. You can load balance as well as possible on the network, but if you do have a burst of packets and you're starting to drop it, you're going to have a very large effect on the job completion time. So one of the benefits of using Ethernet, we see that some of the competition, they're pushing these proprietary networks where you have these islands of closed technology, and you'll see in some cases there'll be like multiple types of proprietary networks that are being used. Ethernet, again, it's an open ecosystem. This is especially important because there are some notable players that are supplying a large number of the GPUs on the market, but you do find that a lot of the hyperscalers, are designing their own accelerators. So for that, they want to be able to efficiently plug into a network, and just in general, you'd much rather have one unified network, one set of spares, one operating policy for the whole network, rather than using different types of networks for different applications. And again, if you look at at some of the competitions trying to do as far as these AI/ML accelerators, they'll have something that looks like a chassis that will have all the chips interconnected with a proprietary interconnect. Next layer up, they'll have that again with a proprietary interconnect to a switch that's only available from a single vendor. Next layer up from that is a different type of proprietary interconnect. So it's really kind of going backwards in time, trying to vertically integrate these systems. With Ethernet, again, it's something where you wind up getting, better performance, and you wind up being able to use the whole ecosystem, including switches from, I think, any GPU vendor, and if you want to develop your own switch or your own ML accelerator, you can drop that in with the same networking technology. So just in summary, again, Tomahawk 5 as far as benefits for AI ML, highest bandwidth, highest radix. Again, the fewer number of switch hops you can get, the lower the latency is going to be through the network. Cognitive routing. So again, a lot of features here, recognizing the fact that the AI ML workloads are very different than standard DC workloads, DC traffic. So you get very high link utilization, adding some intelligence, especially this global load balancing to your routing decisions. Burst absorption, so this fully unified buffer winds up getting you much better burst absorption than some of the competing architectures. And then finally, as far as in-band and out-of-band telemetry, we can do, again, we have 6 ARM cores on chip that we can use to summarize data. We can use that to send the data to a centralized collector if you want to do things in an out-of-band fashion. And then in-band, we can both insert data in real time on network probes that would follow the same path as your standard networking traffic, and we can also just insert that on live traffic as it flows through the network. So overall, Tomahawk 5, you got the benefits of Ethernet as far as the open ecosystem, plus the bandwidth and a lot of features that will accelerate and actually give you the highest performance AI ML networking.